Okay, welcome to this video here on the 2010 higher level Section C question 1. Alright, so the accompanying map located on the back of Section A shows ground contours at 5 meter vertical intervals. ABC is the center line of a proposed roadway. The section of a roadway between A and B is level and an altitude is 60 meters. The section from B to C has a gradient of 1:30 rising. You want to be underlining these keywords. Use side slopes 1 in 1.5 for cuttings and 1 in 2 for the embankments. Complete the earthworks necessary to accommodate the roadway on the northern side. So the ones on the south, on this side, have already been done. Part B. On the map, D, E and F are outcrop points on the top surface of a stratum of ore. The line EG is the strike line for the stratum and has been constructed as shown. Part I. Determine the dip of the stratum. Part 2. A vertical borehole at F reveals a vertical depth of the stratum, of 25 meters. So that means that the stratum has a vertical depth of 25 meters. It says determine the actual thickness of the stratum. So this these two set squares here, it'd be tricky now to get them up here as edges, but they have a vertical distance of 20 apart, but that's not their perpendicular distance. So you're basically being asked for the perpendicular distance. Alright, now, so we're going to start with part 1. So we're going to look at the contours here, and we know the roadway is level at an altitude of 60 meters. At 60 meters. So now, where the 60 hits the roadway, there's going to be a change in whether it's an embankment or a cut. Right, so there's a 60 there. So there is. Now, all in this area is cuts because 65, 70, 75, 80, 80 and so on and so forth. Now, we're going to draw lines parallel to the edge of the roadway. And we have to figure out what's the distance between the lines. The first thing you do is to scale. Don't take it for granted it's 1:1000. 2016 is a perfect example. Right. The road is rising in 5 meter vertical intervals. 5 meters equals 5,000 millimeters, so 5 meters, 5,000 divided by 1,000 equals 5. Now, the cutting ratio, so for every 1 unit you go up, you go over 1.5. So for every 5 meters in real life you go up, you're going out 7.5 meters. So on your sheet, for every 5 million you go up, you go out 7.5. So we're going to take our set squares and we're going to draw some parallel lines and perpendicular lines. So we're going to draw in a line there, perpendicular to the edge of the roadway. I'm going to mark every 7.5 along there. So nearly start off wrong. So every 7.5. So we're good to go. Right, now we're going to draw lines parallel to the edge of the roadway now. Okay, excuse the background noise. Now, the numbers rise in numerical value for cuts the further you go out the road. So this is 60, this is 65, this is 70, 75, and 80. And they don't go any higher than that. So 60, where the 65 contour hits the 65 line, okay, we're going to mark it in. So there's the 65 line. Where the 70 contour line hits the 70 altitude line, 70, 75, 80, 80, it's going back down, 75, 70, 65, and 60 there. Alright, and then we're going to, freehand sketch them in. Okay, and the tadpoles going away from the road. This area here is an embankment, alright, because the numbers are lower than 60. Alright, so the numbers are lower than 60. For the embankment, it says 1:2. So for every 1 unit you go down, we're going out 2 units. So 1 unit is equivalent of 5 millimeters. So we're going out 10 millimeters from the side of the road. So sliding set squares. Okay, I'll move that up further. We're going to slide this on, and we're going to mark 10, 10, 10, 10. Now, this is 60, this is 55, 50, 45, and we won't need 40. So that for embankments, the numbers get lower in numerical value the further out from the road you go. So there we go there. So 55, the 55 line there, where that hits the contour line 55, that's a point there. The same with the, just 1 second there now. Okay, so we're back at it there. So we have the 55 point mark there, the 51 mark there, and then the 45 one marked there, and that's, we don't really need any more. Alright, but also just to draw your attention, in this area here, it's an embankment, and this portion is 55. Alright, so what we're going to do is, like, it's going to interlap, this portion of the roadway is going to interlap with that one. So what we're going to do is we're going to continue on the 55 embankment line to this area until it touches the contour 55. Okay, light freehand sketch that in. Okay, now same with the contours up here. The 50, okay, 50 and 45. And then the 41 will be off the page there. They wouldn't be too strict about that. That's, oh, you can't even see it there. So you can't on this. Alright, don't forget your tadpoles. They go in towards the road. Now, we're going to deal with section B to C. Now, B to C is rising, okay, at a ratio of 1:30. So, what that means in real life, for every 30 meters you walk, alright, so for every 30 meters you walk, the road rises by a meter. So if I walk 60 meters, the road has risen 2 meters. Alright, if I walk 150 meters, the road has risen 5 meters. So the problem here is we don't have an altitude for point C to do this. Okay, so how we solve it is from point B, we are going to measure 150 millimeters from point C. Okay, and what that'll do is give us a point that is a defined altitude above. So we're going to measure 150 millimeters. Excuse any background noise here. And this point X is at 65 meters, because B is at 60 and no, sorry, I done that right. So for every 30 meters we rise, or for every 30 meters we walk, we rise 1 meter. So if I walk 150 meters, I rise 5 meters. So this point X is at an altitude of 65 meters. And right, because this is a sloping or a rising road, or a falling road also is the same thing, the lines we're going to do for getting the points on the earthworks are going to be slanted. That you'll see if you skip forward roughly 10 minutes, you'll see what I mean, 10-15 minutes. Right now, this is going to be an embankment, because the lowest point in the road is 60, the highest point is 65, and all these numbers are below that value. So for an embankment, you start your cone at what you call it the the highest end of the road. Okay, so the cone is going to go here. The ratio for the cone is 1:2 for the embankment. So what you have to do, okay, just give us one moment there. Okay, so if the cone is at the highest point of the road, and this is the lowest, so this is at 60, alright, and this is the road here. This is at 65. So you've got to figure out the altitude of the cone, which is 5 meters. And then apply the height of the cone into the formula 1:2. So that means that the radius of the cone is 10. And these are going to be the lines going like that upwards. Right, so from this point here, I'm going to set my cone to a radius 10 millimeters. Okay. So I'll set it to 10 there. Put in my compass. And I'm going to draw in my semicircle. Now, alright, we'll extend on. Okay, over here we have to extend on the roadway a little bit, pretend it's straight. Alright, bring point B to here, because they're earthworks intersecting each other. Now, join what you call it, take the point B and draw a line that's tangential to the semicircle. Now, you don't have to go through the method of actually drawing in a tangent. That's going to take too long. So that cone's altitude, or this line's altitude rather, is at oh shucks, that's at 60. The lowest point there is 60. Just one sec there. So think about it. I'm just going to pause the video. I've got the numbers mixed up in my head now. Okay, so brain freeze over. Alright, so that's at 60 meters there. Right, now the next thing we're going to do is draw lines perpendicular to that line there. So 10, 10, 10, 10, 10, 10. And then we're going to draw in lines parallel to the first one. Okay, so 60, 55, 50, 45, 40, and that's enough. Alright, now, this is the 61. The next one, 55. Alright, so we go up to the next contour, and over to here, and I gotta bring this one on before, I gotta bring that one on. Okay, so that's at 60, and this one here, 55, okay, 50, okay, just 1 second there. Okay, now, 60, 55, 50, so there's two 50s here. 45, alright, or there's another 55 here, so it drops back down to there, okay, and then to there again, it goes back up to 50 here, and then 45, 45, back down to 50 here, back down to 55 there, so to there. So we're going to join them in. Right, and there's our embankment there along that line there. And now, where those two sections intersect is a point there, and that's the line of intersection between the two earthworks. So the tadpoles go into the road. Alright, so I'm going to, well, I'll heavy in that line later. I'll pause it and do it in neatly. Right, the next part of the question is what you call it to do. Determine the dip of the stratum and get the actual thickness. So this strike here is a true length. Alright, if you look along the true length of a line, it projects as a point. And once the line projects as a point, the surface it rests on projects as an edge. So I'm going to continue this line on. So in order to see the dip, I need to see the horizontal plane as the x1, y1 line, and that triangle there is just a single line. Okay, so that distance there can be anything I want. It's just perpendicular. That line is perpendicular to line EG. So x1, y1. Alright, and I'm going to bring D on. Okay, and I'm going to bring F on. Now, F has an altitude of 80 because it's on the contour line 80, even though you can't see there. E has an altitude of 65 and D has an altitude of 55. Alright, so from this x1, y1 line, we're going to go up. Alright, we're going to go up in 5s here. Now, I'd suggest leaving a bit of space there, starting up just a little further. Alright, because you'll need it. Okay, so it starts at what we say it starts at. D starts at 55. Okay, so 55, 60, 65, 70, 75, 80 is the highest one. Okay, so I've marked in those dots along there. Okay, now, this is, what I said, this was 55, I'm missing one there. Okay, 55, 60, 65, 70, 75, 80. So F is at altitude 80. E is at altitude 65. And D is at altitude 55. So all these points joined together should give me a straight line if I've done it right. Okay, and they do. Now, the dip, okay, is the angle between this line here, and the x1, y1 line. So, if you want to get the angle, you can just draw a line parallel to that and measure the angle here. Okay, so the angle of the dip, or the stratum makes to the horizontal plane, is 23 degrees. Okay, 23 degrees, the dip. Okay, so remember this line here, this one is parallel to EG, the x1, y1 line is perpendicular to it. You can start that wherever you want, alright. You can start your 55 really and truly wherever you want if you really understand this stuff. Okay, and these spaces have to be 5 apart. And then F, it goes to its relevant height, same with E and D, and they should join together as a line. Now the next thing it says is a vertical borehole at F. So a vertical borehole at F reveals a stratum of 25, the depth of stratum of 25. Determine the actual thickness of it. So what that's saying is go down 25 perpendicular to the x1, y1 line, so back at 55, draw in a line parallel to the top one. Okay, so draw in a line parallel and then measure the perpendicular distance. So you're using your sliding set squares there. Okay, so we can measure this is the thickness T. And it says determine the actual thickness. So write in thickness there, and I would always measure it and write down the answer. And write it in meters. So the thickness is 23 meters. Okay, and that's the question. Well, I promised I'd sketch it in to make it look right, so it's easier to see. So I'm going to pause this. So that's the finished item. Okay, cheers, thank you, bye bye.